Awesome. Yes, so we welcome everyone in the virtual space. And, you know, there are advantages to the virtual space that, you know, we could have this team from Howard University with us this morning. I do see Dr. Cummings, Professor Cummings. Let me try to find you and make you a co-host. Okay. Here's out. I'm not seeing that option. You can have several co-hosts, I imagine. I'm not seeing it here.
We want to make host?
Stephen Cummings.
Okay.
Thank you. Okay, great. Thank you so much. All righty. So as I was saying before, we have a power team from Howard University with us this morning. And so in terms of how we're going to do it, we will have Professor Cummings start, and he's going to share on his research entitled Adding Steric Bulk to Antibiotics to Disrupt Cell Wall Formation. And then he'll be followed by Professor Timothy Ramadhar, who will be speaking about the crystal sponge method, enhancing the technique for small molecule structure elucidation. And so Professor Ramadhar has some Caribbean roots. His parents are from the Twin Island of Trinidad and Tobago, or friends down that side. And so he has been in the Department of Chemistry at Howard University. He's been there since 2018. He has done a lot of work in terms of synthesis, etc. And so he will be speaking to us about this method that many of us who are natural product chemists are like totally excited about. Yes. And so, but as I said before, it will start out with Professor Cummings. So let me say a few words about Professor Cummings. He completed his bachelor's in neuroscience and chemistry at UC Santa Cruz. And so, but he launched more into the chemistry as time went on. And so he went to UC at Riverside, and he was a part of a team that successfully isolated a perfluorinated carborane acid, which is clearly of great value to us and to the entire world, as a matter of fact. He joined the chemistry department at Howard University in 2017. And so he's doing a lot of work in terms of hydrogenation methodologies. And so he will be speaking to you as well. And also on camera, we see Kenisha Johnson, who is one of our graduates from the University of the West Indies Mona campus here in the Department of Chemistry. And we are very proud of her and her accomplishments. And so I want to give them as much time as they need in order to go through and to talk to us about what it is that they have been doing in terms of their research, as well as what the opportunities are for the rest of us. Oh, hello there, Professor Matthews. Good to see you and meet you virtually. Awesome. Good to have you all in the room with us this morning. So I'm going to just hand straight over to Professor Cummings. I don't know if Professor Matthews, you want to say anything initially, and then we launch into it?
Okay, let's go ahead and launch into it. Hi, I'm Dr. Matthews. I'm the director of the Graduate Studies Program here at Howard. Glad to meet you. Let's go ahead and get started since we're kind of short on time. I'll talk toward the end. Okay. Go ahead, Dr. Cummings.
Awesome.
All right, good morning. So let me get my screen shared. All right, so I'm going to talk just about one of the projects we're working on. It's a collaborative project with another colleague here in chemistry, Dr. Kim. So a lot of this comes from from his research, and we're expanding it now. And so I'll go through that a little bit. So we're all familiar with the idea that more and more bacteria are becoming antibiotic resistant. And this is clearly becoming a challenge that we need to address because one of the most common antibiotics that's used, it's considered the last source, is vancomycin, but as bacteria become resistant to it, we need to find new ways to challenge these bacteria. So the vancomycin is a glycopeptide type of protein, and it's unique in that it has, oh, I need a pointer, sorry. It has, its backbone is cross-linked, making it a very rigid backbone. And that actually kind of, if you look at it, it gives it like a claw structure. And this is something that is going to be useful for defeating bacterial infections, as we'll talk about here in this slide. So all bacteria have a cell wall, whether they're gram-positive or negative, that consists of a that has this peptidoglycan chain that, darn. You have this peptidoglycan with this peptide down here, and the vancomycin actually latches on to this D-alanine dipeptide down here. And so that actually disrupts this transglycosylation step where you form this very large polymeric structure that ultimately makes up the cell wall for bacteria. Now what's happened is, what's leading to some of the disruption to the to vancomycin is this D-alanine. It gets exchanged, there's been a mutation that has led to that should not be D-alanine, that should be DLactate. I apologize on that. So a DLactate, and that causes a significant disruption in our mode of bonding. Oh, I'm actually ahead of myself. Forgot to talk about the mode of action. So how does this work? The D-alanine, what happens is the claw-like structure of the vancomycin coordinates around this D-alanine through hydrogen bonding between the dipeptide here and that rigid backbone structure. And so it locks onto place, and it's has very high activity to prevent the lipid 2 protein from doing transglycosylation and transpeptidation, essentially limiting cell wall growth, and you get a porous structure, and the bacteria just can't survive. What happens in the resistant one, this is the correct slide I was talking about, is that D-alanine gets replaced by DLactate. And this DLactate, you lose one of the main hydrogen bonding, because now you have instead of the NH2 group here that can coordinate to this ketone, you no longer can do that, and essentially you have a 1,000-fold decrease in binding affinity, and essentially lipid 2, the main protein for transglycosylation, just can push off the vancomycin and make the large polypeptide cell wall. So what's been done since then is there's been some research in modifying various functional groups, primarily this functional group out here, or in the disaccharide functional group, which is the one we're going to talk about a little bit. So vancomycin they all have this sugar, but vancomycin terminates with an amino group. There's been some research in changing that off the amino group with various side chains. And what they have found is that you actually can get a significant increase in biocidal activity. For example, we have ortroviacin, which is telavancin and dalbanavicin. These are all commercially available now. And we can see here the vancomycin requires about 1 gram to essentially of material for a full course to kill non-resistant bacteria. But these newer ones, they are not only effective against the non-resistant bacteria, they're also effective against bacteria that contain this DLactate mutation. And you also, more importantly, you need a much lower dose, right? And so this is where my colleague came in, Dr. Kim. The research he did was kind of trying to identify why does this side chain here make these particular compounds, these particular generations of glycopeptides far more effective, right? And so what they found, let me go ahead. What they found was, or what we know is during the cell wall formation, you have this, the lipid 2 cross-links these peptide chains, all right, make a more rigid structure, which that's what ultimately gives that cell wall its structural uniformity and prevents material from going in and out. The glycopeptide, when you have that DLactate, the glycopeptide can't really bind here. Right, and so the question is, what's really happening? And what Dr. Kim did through a series of solid state NMR studies was find out that this particular side chain actually is binding to this cross-link bridge prior to transpeptidation. So you can't form that bridge. And so we'll talk about that. And it's happening because you actually have like this crevice or a finger-like structure that's coming out, and it's wrapping around, again, through a mixture of just intermolecular forces and potentially some other intermolecular interactions, primarily just basic dispersion forces, but it's wrapping around, preventing that lipid 2 from doing the transpeptidation. The important research that they did find out of Dr. Kim's group was, as these side chains get longer, the efficacy goes up of the antibiotic behavior. So up to about 9 carbon units, and you get the maximum behavior. Once it gets too long, then it can no longer block that side chain or the cross-linking bridge. And so you lose antibiotic behavior. So about 9 carbon units is really the max. And that doesn't really matter whether it's an aromatic or an alkyl group, but they did find slightly higher efficacy with the aromatic groups, as we can see here with ortroviacin being more effective than the dalbavancin. So this suggests that steric bulk also plays a role in addition to just intermolecular forces. And so that's where our group's now coming in. I wanted to show this part. I forgot about this. So we have the vancomycin, just pure vancomycin. What's happening here is that you don't have that side chain. And so when you have that dipeptide, you really can't get any coordination over this cross-link bridge. And that ultimately, like we said, the lipid 2 can just push it off. So when you have this, you can overlap that cross-link bridge. What's happening is, as you form this peptide, when it undergoes the transpeptidation, lipid 2 can't form the transpeptidation, and it creates this loose structure. And that loose structure ends up being the format that the subsequent cell wall is going to follow. And so you just get a very porous cell wall at the end of the day, again, ultimately leading to bacterial death. So what our group wants to do is ultimately modify that side chain to be more sterically, or to have larger steric bulk, as well as better intermolecular interactions. So like I said, we're really limited to dispersion on the current derivative. So we think we can improve by using carburyl clusters. Right? There's two ultimate reasons we think carburyl clusters will be more effective. The first is that they are sterically bulky. So we're going to be working specifically with these dicarboranes, which come in 2 flavors, ortho-meta, or 3 flavors, ortho-meta and para, if we're working with the neutral dicarboranes where there's 2 carbon units. And they're like I said, they're sterically bulky. So if you imagine a benzene ring spinning on its axis, this permanent 3D bulk would be about 128 cubic angstroms. These materials here, the carborane occupy about 145 cubic angstroms. So it's actually even larger than an adamantyl group. So they're very large. The other thing that makes them really kind of unique, and it's small, but they're finding it to become fairly important, especially when we are talking about, say, metal organic frameworks, is that there's hydrogen bonding through these BH vertices. I guess I should describe that. Wherever you see a blank vertice, I know as organic chemists, we always want to say that's a carbon with implicit hydrogens. In the case of carborane chemistry, that's actually a BH vertice. So with one hydrogen coming off. So because you end up with this hydritic bond, and that's allowing for hydrogen bonding with nitrogen, oxygen, and other halides. And so we think we can take advantage of that by improving the hydrogen bonding with this, our side chain, being able to hydrogen bond here with this amine, the nitrogen and oxygen here. And so you get ultimately more effective behavior. The other advantage we believe that this will impart is that because these are man-made product, bacteria should have a limited way to actually deal with this carborane because they are very non-reactive and do not fall apart very easily. So that's one of the reasons why we're pursuing this. And so this is Dr. Kim, who did the basis of the research determining the secondary mode of activation. These are two of the students in our group, Brittany, who's pursuing her master's right now and is going to follow up with us for a PhD. And then Echo, she just finished her undergraduate here and now she's at Howard Medical School. So they worked on this project, starting to identify some of the precursors. So this is just some of the precursors we're interested in. And you'll notice they all have a common theme of an aldehyde present, because ultimately we want to be able to undergo a shift-based condensation with that terminal amine of that disaccharide. And we have various chain lengths. So obviously a single carborane, which would be roughly the same length as a aromatic group. And ultimately, if we can get two of these carboranes in, what is the potential maximum efficacy we can achieve? And so that's what we're looking at. We're also looking at any electronic influences we can determine, whether it's a carbon-bound aromatic group. So you would actually have these aromatics become electron deficient, or if we bind it through the boron, you would actually make these aromatic groups a little bit more electron rich, thereby changing the intermolecular forces available. And we know that intermolecular forces can make a great deal of difference with respect to the efficacy of many of these drugs. So I'm just going to go through two quick examples. Essentially how we're making these in our lab is we start with this nido compound, an open-faced boron precursor, and we just mix it with various ionic liquids. We have to determine which ionic liquids work best, but you can take the alkyne and you get dehydrogenative cage closing. So there's actually two hydrogens on each of these boron vertices here, and they will react. They can be deprotonated by the ionic liquid, and then you get your alkyne insertion. We did find this actually works with propargyl alcohol. So we have isolated this product here. That's this NMR. So decaborane is noted by these three main peaks here. And during the cage closing, we get this symmetric structure. We have a plane of symmetry right down through here. And so we see our four main boron peaks in this particular NMR here. So we've isolated this. We're going to go ahead and react it with PCC to ultimately get our aldehyde. We'll give that, and we'll then coordinate this to vancomycin for follow-up characterization. So this is where this particular step is at. The other one that is probably the most interesting, again, because I said you want to have ultimately 9 carbons long. And so we want to be able to get an aromatic and a carborane coordinated to give us that rough 9 carbon unit. This is where we've had significant struggles. These are the two most active ionic liquids that are known in literature for this particular cage closing. And unfortunately, what we're seeing is just pure conversion to boric acid. So there's our initial thoughts were either there's some sort of reaction due to the aldehyde, or it's too electron deficient through this alkyne. And so we're not getting any reaction. One thing we have seen, and this result actually just came out last night, this morning, so I don't have the NMR to show it, but we did protect our aldehyde, and with the dimethoxy here, or dimethanol protection, and we do see some conversion. It's not fantastic conversion, but we are seeing some conversion. So we just need to improve our method development here to isolate this, and then we can deprotect back to the aldehyde. And we don't think it's just an electronic structure, because we were able to get some conversion, again, not complete conversion, using para-ethynyl nitrobenzene, and we were able to get some conversion. Again, not fantastic. So we are doing method development to try to figure out how to improve this to ultimately get all of our desired compounds here for follow-up studies in the future. So with that, sorry to be really kind of rushed on all of this, but with that, I'd like to thank my group. This picture is actually from right before the pandemic started. So some of these people have graduated. For example, Jaquestas, she's now at Berkeley. Tanda and Halima, I think, are finishing up their studies and graduating. Chemo's just graduated. And as I said, Echo, she's now at Howard Medical School, working there. So, and then the main person working on this project is Brittany. So with that, I will finish up. If anyone's interested in follow-up, please go ahead and ask questions, and I will take them.
Thank you so much, Professor Cummings. That's absolutely interesting and fascinating work. Anyone has any questions? Go ahead, Marcel.
Oh, good morning, and thank you for your presentation, Professor Cummings. I was just curious, why is it that we're specifically you're zoning in on antibacterial activity, where I see they're speaking about these type of compounds describing have opening old locks with new keys, or new keys with new locks with old keys. It shows that there's a wide variety of activity and application. So why is it that you're specifically zoning in on antibacterial? That was my question.
Oh, that is a fantastic question, Marcel. Yes. No, this is just one project we're working on. So Dr. Kim, this is part of his research when he came to Howard, is on the mode of action and trying to find new ways with the antibiotic behavior of vancomycin. But there absolutely is research into carbarynes for a variety of other biomedical applications, such as estrogen agonists and other antibacterial activity, because they are, I didn't mention, they are extremely lipophilic. So we know they can get into cell membranes fairly readily. This is just the one of 4 main projects that our group is focusing on.
All right.
Yep.
Okay, great. Thank you so much. I'm going to ask anyone else who has questions, you hold the questions, and after we go through with Professor Ramadhar. Thank you so much, Professor Cummings.
All right. I'll go ahead and share my screen. Great. Can everybody see my screen?
Yes.
Yeah.
Excellent. Let me just change the pointer here. Okay, great. Well, thank you very much for the opportunity to be able to speak with you all today. So today I'm going to be talking about a major research thrust in my lab, which is development and application of the crystalline sponge method. Okay. So X-ray crystallography is one of the most powerful structural determination techniques available. With a single crystal and as little as a few hours, you can be able to determine the structure of a molecule. You can be able to determine how all the atoms are connected together, and you can also determine their 3D configurations. So you can basically determine relative and absolute steric configuration, absolute steric configuration being a chirality. And you can also determine how these molecules are packed together in 3-dimensional space within a repeating crystalline lattice. Now, one of the main limitations of X-ray crystallography is the requirement of a crystal. And if you're dealing with liquids or amorphous solids or compounds that crystallize poorly or crystals that poorly diffract, then this technique wouldn't be typically amenable. However, Professor Makoto Fujita's group came away with an interesting way in which to circumvent these limitations, which is called the crystalline sponge method. And it really involves forming a preformed crystalline matrix that is based off of zinc iodide and TPT. TPT being the ligand, which is tris-4-pyridyl-1,3,5-triazine. And so in order to grow these crystals, what you do is you solubilize the TPT ligand in nitrobenzene, and then you layer on top of that a solution of zinc iodide in methanol, and then you let that sit at room temperature for 7 days, and then you're able to isolate crystals that are at the interface of those solvents. And then the next thing that you have to do is to exchange out the nitrobenzene for cyclohexane. And that's because nitrobenzene has a strong affinity for the pores, and it's going to be hard for the target molecules to be able to displace the nitrobenzene. So then you take these crystals, you put it into cyclohexane, heat it at a 50 degrees centigrade for another week, and then you're able to get crystalline sponges that are viable for the technique. What you do next when you want to do the crystalline sponge method is that you take one of these crystals, you put it into a vial, you have the target compounds that you want to analyze in microgram to nanogram quantities, solvated in cyclohexane with a little bit of halogenated solvent to facilitate solvation. And then you have like a 50 microliter solution of that, you add it to your crystal, you seal the vial up, you put a needle through it, and then you stick it in an oven at 50 degrees centigrade for 2 days. And then what happens during that period is that the solvent's going to slowly evaporate, and the target molecule will eventually enter into the crystalline sponge, be able to kick out the solvent, and through a thermodynamic equilibration process, become ordered and stabilized within the host framework. And then you can take this host-guest complex and subject it to Xray crystallography in order to determine the structure of the target molecule. Now, this technique has been applied multiple times since its original inception in Nature in 2013. So the Fujita group was basically able to use it as a molecular flask to follow the mechanism of a palladium-mediated aromatic bromination of this palladicycle here. So they were able to include this palladicycle during crystal growth, and then they were able to soak in NBS or N-bromosuccinimide. They were able to observe the intermediate from transmetallation, and they were also able to observe the reductive elimination to give you the brominated compounds. And they were able to determine that this goes through a palladium 0,2 cycle rather than a palladium 2,4 cycle. Professor Buchwald at MIT was able to use this technique to reevaluate the structure of a trifluoromethylthioylation reagent. So they thought that this was the original structure here, where the trifluoromethylthio group was on iodine, but they found it then to be on oxygen. And of course, it would be a difficult way to, it would be difficult to use NMR to try to figure out this one out, but they were able to use the crystalline sponge method to unambiguously determine this. And the Fujita group is also able to observe the regioselectivity of oxidation reactions on alpha humulene. So you have these 3 alkene bonds here. If you were to treat this with MCPBA, where does the oxygen go? So they're able to track these sorts of products through the crystalline sponge technique. Also, the crystalline sponge method has been applied to the analysis of a variety of natural products, as you can see here, and it's been, particularly useful for C2 symmetric structures such as alatinine and acerinon, which we'd imagine be a little bit difficult sometimes to look through, to analyze through NMR spectroscopy. But the real power of this is that you're able to determine the absolute configuration or the chirality of these molecules through the crystalline sponge method, which you would imagine would be difficult through NMR or chiroptical analysis. So of course, when this paper was reported in 2013, there was a lot of excitement in the field, particularly from organic chemists and natural products chemists. They really wanted to try it out, and they did, and they ran into quite a few issues. So it is an operationally tough method to perform. The real tough part really is not only including the compound, but actually growing the crystals and exchanging out the nitrobenzene for cyclohexane, because basically as soon as you try to do that step, the crystals basically all shatter. And it's also time consuming to perform too. So it takes 2 weeks to synthesize the crystals, 2 to 3 days to do the guest inclusion, 2 to 3 days to do the crystallography, and a few days to do the refinement. And it might take 3 weeks or so to realize that you weren't able to get your compound inside of the crystalline sponge. And crystallographers also had a lot of issues with the data quality that was reported by the Fujita group, and that all culminated to the misassignment of a natural product here called myacosine A. They wanted to figure out the stereochemistry of the central methyl group right here, and you have a 50-50 shot, right? It's either going to be R or S, and they got it incorrect. And so they had to publish a core addendum in Nature, which really dampened enthusiasm for the technique. However, when I was a postdoc in John Clardy's lab at Harvard Med School, I really thought that this technique had a lot of promise, especially for organic compounds and natural products. And I wanted to see what I could do to try to improve the technique from an operational point of view, and also to instill more confidence in the crystallography by formulating a full set of crystallographic guidelines. So the first thing that I decided to tackle was to try to improve the synthesis of the crystalline sponges. And I was able to do that simply by swapping out the nitrobenzene solvent for chloroform. And so what I was able to do was to solubilize TPT in chloroform and layer on top of that a solution of zinc iodide and methanol. And then you let that sit at room temperature for 3 days. And then you're able to get sponges that are viable for the technique. You do get a mixture of different kinds of morphologies. You get sheets, you get twin crystals, and you get these rods or prisms. And these are the kinds of crystals that you want for the technique. So I was able to reduce the synthetic time from 2 weeks to 3 days, and it avoids exposing the crystals to high temperatures, which is important because the higher temperatures can degrade crystallinity. And not only that, you avoid the use of solvent mixtures because you can imagine if you're doing the refinement process and you have a molecule that is aromatic, there's still the potential to have residual cyclohexane inside of the crystalline sponge through the Fujita protocol. And it can be easy to confuse cyclohexane for benzene, especially if there's a lot of disorder. And then in terms of the soaking experiment, what I do is I take a crystal, put it in a vial, and add neat guests, so a neat liquid, and add enough to be able to submerge the crystal. This is also done by the Buchwald group at MIT. It's really the easiest way to do this, and you just soak it for 2 days. And we're able to take these crystals of the synchrotron, particularly the Advanced Photon Source, or Argonne National Laboratory, using the ChemMat CARS beamline. And we were able to include different compounds inside of the crystalline sponge. We were able to put in transanethol, biazolene, which is a brilliant blue liquid. And we were also able to put in a chiral molecule, 1R- methyl acetate. Now, we were able to get good crystallographic data. This is the main statistic that you want to look at. This is the R1, the basic agreement between the experimental electron density map and the calculated electron density map. And there's good agreement. You basically want these to be under 10%, and they are. The most interesting case here, though, is 1R- methyl acetate, which is a chiral oil. And through this technique, I was able to determine the absolute configuration of this oil through Xray crystallography unambiguously. So it really demonstrates the power of the method. Now, I want to show you this asymmetric unit of the inclusion of 1R- methyl acetate inside the crystalline sponge because it's a special beast. So upon trapping this in the crystalline sponge, there was a single crystal to single crystal transformation where the space group symmetry dropped from C2OC to P21, and the unit cell size, at least the C-axis, doubled in size from 33 angstroms to about 67 angstroms, causing us to get a huge unit cell with a lot of atoms. And actually you have over 500 non-hydrogen atoms inside. So this became like refining a little protein. And it took me about 3 weeks to be able to refine this fully, but I was able to do so and locate 14 molecules of 1R- methyl acetate in the asymmetric unit. Through analysis of these systems as well, I was able to formulate a full set of crystallographic guidelines. I'm not going to go into this in great detail, but we were able to look at it all the way from crystal selection and evaluation to data collection, processing, being able to phase to get the initial structure. And I talked about how to go about refining the entire system. And I was able to do other kinds of granular analysis on the actual single crystal transformation process. And that was published in Acta Crystallographica section A. Another thing that we wanted to focus on was what would happen if we changed the off-terminal halide ligand from iodine to bromine or chlorine. And we wanted to do that because X-rays interact with electrons, and there's a lot of electrons in iodine. And that would cause the host to contribute greatly to the overall X-ray signal, which we call the structure factors, which could potentially drown out the signals from the guest. And so we thought, well, what if we reduce the electron count, changing iodine to bromine or chlorine? And then if you were to do that, then you reduce the electron count of the host and potentially reduce its contributions to the X-ray signals, and allows you to potentially see the guests better and to be able to refine it better. And so we were able to synthesize these crystals very easily, but instead of using zinc iodide, using chloride or zinc bromide, and we were able to synthesize these crystals in a week's time, and you get high quality crystals. We were able to take 1R- methyl acetate and soak it in there for 2 days, and we were able to collect these structures at the synchrotron, and we were able to successfully observe the 1R- methyl acetates in each of these asymmetric units for the bromide and the chloride systems. And it was easier to be able to locate the guests and refine it. But there's also one big advantage too. Remember, take a look at, this is the case of including 1R- methyl acetate in the zinc iodide sponges. And you can see that this is a huge system that took 3 weeks to refine. The single crystal to single crystal transformation for the zinc bromide and zinc chloride systems wasn't as extensive. The symmetry didn't drop as much. It went down to non-centrosymmetric C2 for both. And the unit cell axis didn't double on the C-axis. So the unit cells were smaller. It was easier to refine these. It only took me a few hours, which is a lot better than a few weeks. So there is an advantage of switching the terminal halide. Even though it looks like an innocuous change, sometimes it can be quite beneficial. And again, we were able to determine the absolute configuration of the molecules inside of the crystalline sponges in both cases. One other thing that we wanted to do was to try to include solids and amorphous, solids and unstable liquid organic compounds inside of the crystalline sponge. So I wanted to try to include E-stilbene, which is the bane of my existence for a while as a postdoc. I had E-stilbene basically saturated in chloroform, added that to the crystalline sponges, let that soak at 3 days room temperature, and I was never able to observe E-stilbene. But I thought about the problem a little more, and I thought, well, I'm using chloroform, and that's a pretty polar solvent. It's a good solvent for E-stilbene, but perhaps it's too good of a solvent. So maybe E-stilbene's going inside of the sponge, but the chloroform is going to help to solvate it and prevent it from forming good intermolecular interactions with the host framework, and you won't be able to see it because it's going to be way too disordered. So I thought, well, why don't I switch the solvent from chloroform to MTBE, methyl terpial ether, which is polar enough to dissolve E-stilbene, but it's not going to be as strong as chloroform. So by switching the solvent, I was able to include E-stilbene at a lower concentration inside of the crystalline sponge, and I was finally able to observe it. And it was very easy to do. You just solubilize this in MTBE, add it, soak it 3 days, and it was good to go from Xray Crystallography. And I was able to include a variety of compounds inside. So not only E-stilbene, I was able to put in vanillin, 4-trifluoromethylphenylazide, and this is not a solid, but it is a liquid inherently, but phenylazides, don't tend to be that stable, and you don't want to have it concentrated. So, solubilizing it in MTBE, we were able to put it inside the crystalline sponge and observe its structure. And this is my favorite example where we were able to include artemisinin, which is an anti-malarial drug and was the subject of the 2017 Nobel Prize in Physiology and Medicine. And at a 0.07 molar concentration, I was able to observe this inside of the crystalline sponge and was able to determine its absolute configuration. Now, the final thing that I do want to talk about is the computational analysis that we performed in a lab in terms of studying the crystalline sponges using DFT calculations. So we firmly believe that it's important to perform fundamental studies on existing crystalline sponges that are in the literature in order to potentially design new frameworks and design them in an efficient way or design them in an effective way. And we also believe in studying these existing sponges in order to facilitate framework selection. So say if you had a target molecule and you had a variety of different sponges, which one should you select to include a certain class of molecules? And it's important to develop a wide array of crystalline sponges in order to maximize the generality of the technique and to be able to include as many different compounds as you can with different shapes and sizes and electronic properties. Because you can imagine for, say, an example like a cross-coupling reaction, right? You won't be able to do every single cross-coupling reaction with palladium tetrakiss. Same sort of deal with the crystalline sponge method. It's important to develop an array of sponges in order to include a wide variety of compounds. So what we wanted to do was to do some computational analysis in order to really quantify and deeply understand the host-guest interactions that are occurring within the crystalline sponges, and then use those insights to perhaps do some further computational studies, say looking at doing some docking studies, looking at finding the binding pockets, and looking at developing new sponges. And this actually ended up being good research to do during a pandemic when the laboratories were closed for the first few months at Howard. So we were able to apply DFT type calculations to the popular Fajitas type sponges. And what we wanted to do was to initially do some geometry optimizations and then be able to calculate the binding energies of various target molecules inside of the crystalline sponge. And we were able to do DFTD, or basically density functional theory calculations with dispersion corrections in Material Studio. And so I'll just talk about one example, which was the first case that we did was transanethol. We were able to do geometry optimizations on this system in Material Studio, and we did it in the gas phase. And as you can see, the red structures are the computed structures, the blue structure is the experimental structure, and you can see that there's a relatively good agreement or great agreement between the experimental structure and the computed structure, and the actual error was low between them. So the RMSD was 0.110 angstroms, which it indicates great agreement between the two. And it shows that we were able to use computation gas phase calculations to accurately reproduce the experimental structures that involve solvents. So it wasn't necessary to implicitly or explicitly deal with solvent in these sorts of calculations. And it also helps to reinforce the validity of the crystalline sponge method because we were able to model the guest molecules correctly, especially, you're dealing with diffuse electron density. You feel like, is this method really real or not? And the good agreement between experimental and computed structures indicates that this technique really does work. So it provides further validation overall for the crystalline sponge method. And the next thing we wanted to do was to determine the binding energy values for the target molecules inside of the framework. And so here's the asymmetric unit, the experimental asymmetric unit for the inclusion of transanethol. You have these three molecules here. I labeled them here as A, B, and C. Below them are the occupancies. And we were able to calculate the E binding values, the binding energies. And in this convention, the higher the binding energy is, the tighter binder it's going to be. Low binding energies indicate weak binding. And so we saw that a molecule A here has the highest binding energy. It's the tightest binder. And what we also wanted to do was to look at something called the B factor, or a measure of disorder in the system. So molecules with low B factors have low disorder and small ellipsoids. Molecules with high B factors have high disorder and big ellipsoids. And we hypothesized that if you had a molecule that was bound tightly, that we would probably have low disorder. And if you had a molecule that was bound weakly, then you have high disorder. And we did note that inverse relationship between the B factor, between the disorder and the binding energy. And then what we decided to do after then is to look at these molecules in detail. And again, A has the highest binding energy, which makes sense if you take a look at a Hirschfeld surface analysis of target A inside of the entire crystalline lattice. And you have the Hirschfeld surface here, and zones that are white indicate good van der Waals interactions, and those that have red zones indicate very tight binding interactions with the host or the other target molecules through van der Waals interactions. And you can see that there's quite a few white zones and some red zones as well. So that does account for the high binding energies that are observed for molecule A. And then we basically looked at the inclusion of other molecules as well, such as artemisinin for trifluoromethylphenylazide. We were also able to look at methyl acetate and vanillin and chloroform, and used these sorts of insights to gain some or use these sorts of approaches to gain insights into their host guest interactions. And so finally, through all this work on the crystalline sponge method, we were able to develop an improved synthesis of the MOFs, making it faster and easier to perform. We were also able to come up with a full set of crystallographic guidelines, which should hopefully instill more confidence in the technique for crystallographers. We were also able to investigate the effects of changing out the iodine terminal halide ligand to chlorine or bromine. we're also able to develop a solvent-based strategy to facilitate inclusion of solid and unstable liquid organic compounds inside of the sponges. And finally, we're able to apply DFT in order to computationally study the crystalline sponges and be able to come up with insights into host guest binding that goes beyond visual inspection. And finally, with that, I'd like to thank my research group, especially Dr. Cardinal, who's a former postdoc, did all the computational work. I'd like to thank my colleagues at Pfizer for their advice and for their support. I'd like to thank Dr. Xiaoliang Zhang, the crystallographer at Harvard, and Yusheng Chen, the beamline scientist at the Advanced Photon Source, for their assistance. And I was able to learn crystallography through them, and they are fantastic teachers, and I am indebted to them because crystallography was an adventure I never thought I would undertake, but the Fujita paper changed everything for me. And I'd like to thank my postdoc advisor, John Clardy, for his support through the early phases of me undertaking this type of research. And I'd like to thank various sources of funding, especially Pfizer, for supporting a lot of this research in my independent career. And I'd like to say, I hope that you enjoyed the presentation, and thank you for joining. And if you have any questions, please do feel free to ask. Thank you.
So much, Professor Ramadhar. I see questions in the chat. I think Dr. Singh Wilmot. Let's
Sure.
start.
Thank you, Dr. Gallimore. Timothy, it's really nice to see your face, to meet you. I've read some about you in Chemistry World. I think you were talking at some point when you were at Harvard about this from way back then. So we make muffs in our labs, right? And we make rare earth muffs from lanthanide. So these are heavy, lots of electron density. And I'm thinking, you know, maybe these sponges that I make with heavy metals and even with transition metals might not be as good. Maybe we need to go to the lighter metals, frameworks and sponges based on lighter metals, so that those won't, the host won't dominate the electron density map. And then, so I asked you to comment on that. And then my other question is, you know, if we could engineer up the interactions within pores, then so we can facilitate host-guest interactions deliberately, then maybe that would also make or fix the guest pores and helping us to slow down the movement and trap the electron densities. I also imagine that you would have to, in solving these structures, use a lot of restraints and constraints, and maybe you have to concentrate the guests inside the pores. Those are just comments you can, but those two questions about what kinds of metals we choose in the framework and engineering the nature of the interactions inside the pores. Would like you to respond to that. Once again, nice to meet you.
Sure. Great to meet you, and thank you for your questions. Those are great questions. So the first one is on lanthanides. I mean, there is the advantage of using lanthanides, because I know there was a paper reported by DePaul, I believe, in Chemistry European Journal, where they were able to synthesize sponges that were stable in water. And of course, there's going to be like metabolite structures and a lot of biological structures that are going to be soluble in water. Water pharmaceuticals as well, and that would just be an advantage. So I mean, sure, I mean, they might have a higher electron count, but if you're able to get water soluble compounds inside of the crystalline sponge, it's certainly worth it. Now it might be, you know, eventually useful to try to reduce the electron count by going to lighter metals, but I mean, I do see the advantage of using lanthanides at this point, especially with their water solubility and stability. In terms of the intermolecular interactions, I do agree. Perhaps there's a potential of attaching some sort of functional groups to help stabilize some of these gases, maybe through hydrogen bonding, through halogen bonding, or even through covalent interactions. And this is demonstrated by Omar Yagi. I believe they used MOF 520, which is based on aluminum, and they were able to use what they call coordinative alignment to be able to covalently trap compounds such as carboxylic acids and alcohols inside of their sponges. And of course, when you do that, you reduce the amount of positional disorder, and then you have higher accuracy on your bond lengths in order to be able to maybe determine some, you know, molecular features of of your compounds more accurately, especially if you're dealing with, am I working with a single bond or am I working with a double bond? Or even, you know, am I working with a carbon atom or a nitrogen atom or an oxygen atom? Because sometimes that's hard to determine with a crystalline sponge method, especially with a ton of disorder. And so, yeah, I would say for the typical crystalline sponge method, it's important to have some sort of ancillary data, you know, to help you determine what the molecular formula might be. But then if you have these other strategies, such as coordinative trapping and covalent interactions, that would make things easier. So yeah, and finally, in terms of the constraints and restraints, yeah, it's important to, you're going to have to use it sometimes. I try to use it as sparingly as possible. And if I do, I try to use soft restraints. So in Shell XL, I typically use things like SADI and SAME. And I talk about which kinds of ADP restraints one should apply. I try to avoid hard restraints like defix and flat as much as possible.
Okay. Okay. Thank you. Thank you very much for that response. Okay, so I do see that Dr. Nelson has some questions. What I'm thinking of doing though, ladies and gentlemen, in the interest of time, because we have students online who are anxious to learn about some of the programs that are being offered, I'm going to hand over to Professor Matthews, and then thereafter, so we can go to after 12 with the questions, but I want to just proceed with Professor Matthews. All right, do you need to share the screen? Do you need to be a co-host, Dr. Matthews? You're muted.
Yes, I do.
Okay, Omar, could you help me out with that, please?
Yes, it's done.
Okay, thank you so much. Okay, go ahead, Professor Matthews.
Okay, good morning or good afternoon. Thank you for setting this up, Dr. Gallimore. I really appreciate it. This is somewhat of a homecoming for me. I was born in Jamaica, left a long time ago. I grew up in New York. Went to Howard as an undergrad, completed my graduate work at Georgia Tech, and I'm back here at Howard as a faculty member. So it's really a pleasure to meet with you and all your students. I just want to give you a brief background about the Department of Chemistry. You know, the Department of Chemistry was the first department at Howard to award the PhD degree in 1958. Since then, we've awarded more than 250 PhDs and greater than 360 masters in chemistry. The masters a little bit more because we started awarding the masters back, I think, in 1918, 19, well before this chemistry building was constructed in 1936. Our current areas of research, it's the traditional areas, organic, inorganic, physical. Of course, there's some crossover areas like materials. We have several faculty members that are doing research in medicinal chemistry. My area is, I'm an organic chemist. I do bioorganic as well as materials. So I do some synthesis of cross-linkers for hemoglobin, as well as some chemical vapor deposition precursors. Of course, we have some analytical professors that do work in Raman spectroscopy, so computational chemist, just quantum Monte Carlo. Dr. Kim, as you heard, was mentioned by Dr. Cummings earlier in his talk. He does solid state NMR, and he has some research in biophysics. So our goal today was to try to give you a flavor for the type of research that's going on at Howard University in the Department of Chemistry, and to encourage you to consider Howard as a next stop in on your educational journey. We have had a long relationship with the University of the West Indies. As a matter of fact, when I was an undergrad at Howard University, several of my teaching assistants were from you. I think I remember one was Ian Hendricks, Kent Bryant. Both have earned their PhDs and gone on to great careers in chemistry. So what we're trying to do is to try and reestablish those ties with the University of the West Indies. We're always had great students from that institution, very well prepared, and they've made significant contributions to research. And stipend that we currently offer our students, it ranges from between 23 to 28,000, and it's over 12 months. So the reason why it's that range is because during the academic year, which is 9 months, the students receive 20,000, and then over the summer, dependent on your funding source for the summer, sometimes it's teaching, sometimes it could be off your faculty advisors research grant. That number will go up to an additional 3 or 8, even in some cases 10,000 over the summer. So we have students that earn anywhere from between 23 to 30K during the time that they're here. And as an international student, you would receive, you'd apply. Once you're, we will accept you, and we provide students with support in the form of full tuition and a stipend. And Dr. Kenesha Johnson is also on this call today. She's one of my former graduate students. She completed her PhD at Howard in my research group. She was a graduate of the University of the West Indies. She'll elaborate on, DC and what it's like to live on a stipend in DC. So one of the things we pride ourselves on is the quality of the students that we put out. Many of our students have gone on to successful careers in industry. We listed a few of the companies, Lubrizol, Intel, Bayer Materials Science, Merck, Coca-Cola. We also have students that have moved on to careers in academia. Dr. Johnson, she's currently a faculty member at Alabama A&M University, but we also have someone else on the call. He's on the Zoom today. Devon Stewart, he's a faculty member at Sacramento State University. We've had faculty members at Spelman, Norfolk State. It's a wide range of opportunities. Also, the government opportunities are also available. Many of our students are at U.S. Patent and Trademark Office, NIH, the Environmental Protection Agency, and also postdoctoral opportunities. Some of our students have gone on to different universities to further their studies. But focusing in on the international students, I just listed a few of them here, highlighted Dr. Johnson, but you can see that many students, even though they come in on a visa, on a student visa, they've been able to remain in the United States. Some have gone back home to their country, their country of birth, but many have stayed and have been able to gain employment in the US. Many of the companies will process the paperwork in order for the students to remain here. So it just depends. It's not a guarantee, but being careful about, if you want to stay in the United States, you just have to be kind of careful about what companies or what opportunities you decide to pursue upon completion of your degree. My information is listed at the bottom of the page. My email address is here. There's a website. There's also an application. If you are interested in the program, one of the things I would encourage you to do is to reach out to me so that we can have a more extensive discussion on the graduate program, what's required. We can also touch base with some potential research advisors. One of the most important things you can do when choosing a graduate program is to make sure that there's a faculty member at the university that is doing work in an area that you're interested in. So if you're interested, please reach out to me. We can set up a Zoom call individually or maybe as a group. I have no problem with that. And I look forward to hearing from you. Here's a picture of our department. This is the chemistry building. It's fairly well equipped. I think Dr. Ramadhar he's the PI on a new X-ray diffractometer that just got funded. I was hoping he was going to expound on that a little bit, but it's a great instrument. We're going to, once it's installed, we are going to encourage all our graduate students to get trained in a single crystal X-ray diffraction. So that's a useful skill, and as well as a very marketable tool when you're seeking employment. Many universities don't have a dedicated crystallographer. So you might be an organic chemist, analytical chemist, but if you have this skill under your tool belt, it would be useful in terms of gaining employment at a university. Are there any questions that I can answer about the program? As I said, please reach out to me, but if there are any brief questions I can answer, I'd be more than happy to do so now.
Thank you so much, Professor Matthews. Any questions, ladies and gentlemen? Please record that email address information. Okay. Dr. Johnson was supposed to say a few words.
Oh, yes. Please, Dr. Johnson, can you share some insight share your experience here at Howard and how you enjoyed coming to Howard in the transition from UE?
Awesome.
Sure. I'm from St. Elizabeth. I went to Manchester High School, did undergrad at UE, of course. And then I worked for 2.5 years at Caribbean Regional Drug Testing Lab. I think the name might have changed. They're right next door to Government Chemists over there in Hope Gardens. After I worked for 2.5 years, I actually visited Howard before I joined them or picked my advisor. So I didn't pick Dr. Matthews because he's Jamaican. I actually visited, and he did say something important. Ensure that you interview the advisor that you want to work with. Make sure you're interested in his project. Also, ensure that you talk to the people in his group, because this is a long-term relationship. It's going to be at least 5 years. So you need to be sure that this is the project you want to be on and this is the person you want to work with. When I got into Howard, I was a little nervous, but I spoke to Dr. Pinnock and he was like, you know, the foundation we give you here, you can do well anywhere. It is true. You're ready. From a theoretical standpoint, from an experimental standpoint, you'll do great at Howard. Let's see, what else do I want to tell you? So for me, Howard should be your pick. I'll tell you why. Culturally, when you leave Jamaica and you move to the States, you want to be somewhere where you feel comfortable and you feel like you belong. It's nice to have people you are familiar with around you. Howard has, from a Caribbean standpoint, there's a lot of Caribbean people at Howard, from both students to faculty. And to be honest with you, especially when you're in a PhD program, you want to have some familiarity surrounding you. So I personally am happy I picked Howard, happy I went there. I've worked in industry and I'm presently teaching. But the thing about getting a PhD from Howard, you have the opportunity to do whatever career you decide to do. You're equipped and you're marketable. The next thing I want to tell you, when you get your advisor or when you pick your group, make sure you understand that this project is now yours, right? Take initiative, read all the literature that's out there on what has been done before, and have your own ideas. You know, you can't sit around and wait on your advisor to tell you your next step. You need to take the initiative and own your project, right? It becomes your life. Now, with the PhD, you're developing something new, so you must know this is not an easy process. I suggest that you understand it becomes your life, no joke. And I recommend though, take at least a day off, Dr. Matthews, yes, take a day off and regroup and come back the next week. Ensure that you publish before you leave. Try to publish at least 3 papers. I think that's reasonable. So you're marketable when you decide to look for a job. Suggestion. If you get in, do not live off campus your first year. It's cold in DC, so you want to be on campus. When you get used to being on campus and the surroundings, then you can decide to venture out, right? Those would be my suggestions. You would be fine in DC. It's like chilling in Jamaica. There's lots to do. I don't know how much of it you'll be able to do, but it's a place where you would be happy. I see Marcel has a question. I hope it's not for me. I'm kidding.
Yes, thank you, Ms. Johnson. I think the students would like to hear about the stipend living, right? How feasible is it to live on, right, and living off campus versus living on campus? So how much is rent or boarding on campus? How much food would cost, living expenses? Does the stipend sufficiently cover it versus living off campus, transportation, rent, food? How does that really compare?
Excellent question, Marcel. Okay, so for me, my first semester, I lived on campus as recommended by Dr. Matthews, which was a great idea. So this is what I would say. I had money enough to send home to buy food, to pay my rent. So the money you get, right? You can pay your rent, buy food, shop if you want. No, you can't buy Gucci bag. But I'm saying, you know, you're comfortable. You're able to live. I have a friend from the Bahamas. She used to live off campus and she was perfectly fine as well. She used to ride a train though. You don't really need a car, to be honest with you, in DC. I wouldn't get a car because the train takes you everywhere you need to go. So in terms of transportation, food, parent, you can do all of that and still have money to play with, even if you want to send money back home for your family. Because I used to do that. I used to send money back home to my mom. So it's more than enough. You can live, but like I said, you can't come by, you know, BMW and all that. No, you can't. It's not money to do that. You're in a PhD program to get to a place where then, you know, you can buy the car cash or buy a house. You know what I mean? So yes, you'll be fine. Marcel, you still have another one?
Okay.
Oh, no, sorry. Both hands, sorry.
Okay,
No,
no
it's
problem.
okay.
Could you just specifically tell me what rent is like? I'm not sure you mentioned. Give me a ballpark of
Okay,
rent.
so I left DC in 2013. Dr. Matthews, you want to take this one?
So Washington, D.C. in the past 20 years has undergone significant change. And here we call it gentrification. It used to be a very large majority African-American city, but it's very diverse now. It's more balanced. So in light of that, cost of living has increased. So most students, and the best thing to do would, I would suggest, would be to live on campus. I don't exactly know what the dorm fee is if you live on the dorm for the first semester. However, after moving off campus, when she says off campus, she moved 3 blocks down the road. So she walked to the building every day. So she wasn't really off campus. She was still around. It was just renting a room in a private house. So most students will get together and rent a house. And you'll have a room, but you'll share the common areas like bathrooms and the kitchen. And the price for that, and of course it varies, and it depends on the size of the house, but the price for that is anywhere from, on the lower end, I would say about $700 a month for a room in a house. And on the higher end, you know, sky's the limit, but I would say that, I mean, around here, maybe $1,300. So it's in that range. So, I mean, depending on what house you live in and with friends, I would shoot for maybe about $700 or $800. However, if I could get some more detailed information on that from some of the current graduate students and get back to you. Now, if you want to live by yourself because you're not used to living with people, then it's going to be more expensive. There's a 1-bedroom apartment build. If you want a 1-bedroom, there's an apartment building not far from campus where many of the students go, and that's going to run you closer to $1,300 to $1,400 on the lower end if you must live by yourself. But you know, there are compromises you may have to make if you would like to have a little extra money at the end of the month. Students do other things like tutoring. You know, tutoring, you might do some tutoring on the side to supplement and things like that. But I would say anywhere from, the minimum is 7. I would shoot for 7 or 8. If you want to share, if you want to get your own place, the minimum is probably, there's some places for 12, maybe 12, 13,
Okay.
14. If you want high end, you're going to be up in 1,800 to 2,300. It just depends on what.
No problem. Yeah.
Sorry, Dr. Gallimore, could I interject, please?
No
I
problem.
have a suggestion, sorry. If you're moving into a house, please do not move in with undergrads. Their lifestyle is different from yours, right? Try to move into a house with some mature people, no joke. I lived in a house with 5 people and it was great. For sure, I barely saw the people who lived in the house, right? And then another thing, be mindful, when you live with other people, you know, everybody is like the cleanest or whatever. This is why I'm telling you, you kind of want to pick mature people. You don't need party going on downstairs. Trust me when I tell you, grad school is different from undergrad. Do not pick a house with a bunch of undergrads. You guys are not on the same level. Pick a house with some graduate people, or unless you know the undergrads and they're mature. But that would be my suggestion for the house with the, you know, with a lot of people in it.
Okay, no problem. Yes, Marcel, you had another question?
Yes, I have a follow-up question. So I'm not sure if he said it. What about living on hall? Like, how much does that cost, the boarding on hall? Or
Okay.
if that was mentioned. And also, I'm sure the students would like to know that is the GRE system still intact versus that you have to do a GRE to come into this university, or is that program now waived where you just apply based on your merit and your degree here? How does that work?
So the first question regarding the cost of housing for the semester in the dorm, I can get back to you with that. I can forward it to Dr. Gallimore, and she can
No problem.
communicate it to you, Marcel. However, the GRE, we would like for our students to take the GRE prior to coming. You don't have to take it prior to coming. It's a recommendation. However, I can admit you to the program without you taking the GRE. However, during your first semester, we'll schedule the GRE for you. So you will take it during your first semester in residence, because we like to collect that data, and we can assist you with scheduling it and taking the exam. That's not a significant issue. It's not something that you have to burden yourself with right now if you're unable to take it in Jamaica, or it's whatever, for whatever reason. I know because of COVID, a lot of schools have waived it, but it's data that we use to collect, and we like to collect and use for our records.
Sorry, Dr. Matthews, do they only do the general, or do they need to do the subject GRE?
You don't need to do the subject GREs, just the general GRE. Thank you.
Okay. Thank you so much. Is there any other question from our undergrads? There are several undergrad students who are on this platform. Undergrads, do you have any questions? New questions from our undergraduate students. Dr. Stewart, do you have anything that you'd like to add or share? We are so proud of you as well as one of our own.
Yeah, thank you. I just came in to be a little fly on the wall. I was so proud, and I'm so thankful for Howard University for doing this recruitment event. I think Howard is such a good place. Like Kenisha, I'm from Jamaica, I'm from Clarendon. I went to Case, spent 2 years at Case, and then I went to the University of West Indies and I got Mona, and I got a degree in chemistry and biochemistry double major. And shortly thereafter, I was on a work and travel program, and I decided to visit Howard University in DC, and I bumped into Kenisha. Actually, I bumped into Dr. Matthews, and Dr. Matthews told me that he's Jamaican, and he said, I have a student from Jamaica here as well. And me and Kenisha had a wonderful talk, and she encouraged me to apply, and I applied and got into the program, and it was really a awesome experience for me as well in the program. You really get prepared, and I underscore everything that Dr. Johnson said in terms of those little nuggets and going through the program. And just one thing I would add is when you are deciding who your research mentor PI is going to be, look on if they have external funding to be able to support your work after the first couple of years, because being a TA, when it comes time to really fully invest yourself in research, can be a little bit distracting. That shouldn't be your primary deciding factor though, but it would be good if you have an advisor who can say, you don't need to TA anymore, you can just commit to being a research assistant, and then you won't have to grade endless amount of lab reports and stuff like that. You can just focus 24/7 on your research. So that's the only piece that I would add. But it's a wonderful institution. You would fit in well as a Jamaican with the community that's there. So I would definitely encourage you to apply. And I'm also available if you have any question that you would like to ask about the experience at Howard. Thanks.
Great. Thank you.
Just to follow up on Dr. Stewart's comment. Don't feel like you can't ask, ask a faculty member, how do you plan on supporting me? Will I have to TA for the duration? Grants come and go. Research grants have a limited life. Some are 3 years, some are 5. It just depends. So a faculty member might be in between grants. But don't be hesitant to ask, will I have to TA for the 4 years? And if you have to, there's students that have TA'd for the 4 years and they're fine. Is it easier? Like Dr. Stewart said, if you are not TAing, sure it is. If you're on a research assistantship, I believe, Kanisha, you didn't TA that much, right? Maybe a semester or so.
1 semester.
Right. So she was on RA most of the time, and it helps. You have a lot more freedom and flexibility, but you also should have some teaching experience because it's useful if you decide, as both of these former students did, to pursue a career in academia.
Definitely. Thank you so much for that contribution. Okay, it is now 15 past the hour. And so if the undergrad students have no further questions, I am going to go back to the presentations, the research aspects of it, to field any questions that you may have for Professor Cummings or Professor Ramadhar, because I'm sure that they also have a schedule and they may have to leave soon as well. So I'm going to hand over right now to Dr. Nelson, if you have any questions.
Okay, Prof. Ramadhar, good presentation, good work, interesting stuff. I just have some simple questions. For example, where you presented the binding energy, are these free energies or enthalpies?
Oh, these are Born-Oppenheimer or electronic energies purely, because for the free energies, you'd have to calculate out the Hessian. You have to get basically the frequencies and do the 0-point energy corrections and entropy corrections. So that hasn't been done. I mean, that would take a lot of resources to be able to do that. And I really haven't seen that being done in the literature. It just seems like people have been using the straight up electronic or Born-Oppenheimer energies for that.
And you're not worried about the entropy factor being, not included in the Born-Oppenheimer?
There might be some influence of it, but I think if you're just comparing everything relative to one another, especially, starting, just the energies of the framework itself, the energies of the guests and the energies in the ancillary guests when you're just looking at each individual guests. I'm not worried about it too much. I don't think it's going to be that huge of an influence, but it could play a little bit of an influence for sure. I think that would be more of a concern if you're looking at comparing, you had a binding energy of maybe like 30.5 kcals per mole and then 30.6 or 30.7 kcals per mole. Then it may be a little harder to compare based on the fact that you haven't accounted for 0-point energy corrections and entropy. But I think for large differences, it should be okay. I think trying to do those calculations in Material Studio, I think it would take a long, long time to be able to analyze those sorts of systems that way. I mean, doing some of these geometry optimizations, especially, we do in 2 rounds. The first round is with looser convergence criteria, and the second round is with much tighter convergence criteria. It takes a while to get those to optimize and converge to the stationary point. So yeah, there is always a little bit of a concern. I mean, if these were smaller systems like typical, natural products, I'd always go ahead and calculate the frequencies, figure out if it's a true minimum rather than being a first order, second order, third order stationary saddle point, which you don't want it to be. But we were just following precedents in the MOF literature, and typically people don't do that.
Okay, so seeing that you didn't go the route of calculating the SCN and to see if you're at 0 imaginary frequencies, how did these people in the literature, how were they able to confirm that they're at the global energy minimum? How did you confirm that you're at the global energy minimum, seeing that you did not assess the SCN to see that, okay, you are at 0 imaginary frequencies?
Right. I don't think people do. That's what I have observed in the literature. At least what I can say is based on the fact that these structures are so close to the experimental structures that we can make the assumption with a low RMSD that it's probably a real structure. that's as best as we can go about that sort of estimation. That becomes more problematic if you have a high RMSD. That could be maybe a difference in whether you actually have a transition state or something that's structurally meaningless, or whether, you know, the potential energy surface around that area is very flat. So you can have large changes in geometry without really changing the energies too much. And so it depends on how the converger, which structure it arrives upon. So yeah, we haven't been able to really determine if it's a, you know, 0 order saddle point, or whether it's a first order saddle point or higher. But again, I think we're just really following a lot of the literature precedent, and they don't do that as well, because I think it's really computationally intensive. But we're just going to go on the basis that it really is, it matches experimental structures very closely. So we assume that it's going to be real. Okay, that's interesting, Prof, because this could be kinetic structures. It's a nice thing that they match experimental though. But they could also be kinetic structures, and not necessarily, because you have a crystal structure, it doesn't mean that it is the lowest energy form of the thing. Correct.
If you probably increase the temperature, it could change to something else, which is more stable, you know, thermodynamic structure. But yeah, it's quite interesting though, that your calculations really match experimental.
Yeah, and that would be interesting too, is to do a dynamic study, right? Then you could take that minimized structure, you can shake it up a bit, different temperatures, and see if you return to the same structure, you get maybe something that's going to be energetically lower. That'd be an interesting thing to try, for sure.
Yeah. Prof, you know, if basis set superposition error was considered when the two things come together, because I see you have your host going into this cavity, and the basis set that they use, of course, there will be some overlap of the basis set, which could give you, you know, a problem with your energy.
Right. So the thing is that we use Material Studio, and we use plane waves, a planar wave basis set. So there's no BSSE. If we were using the Popel, I guess the Popel basis sets like in Gaussian 6-1. Then yeah, there is basis BSSE errors, and you have to do counterpoise corrections and all those sorts of things to take care of that. No, that's the advantage of using Material Studio with these plane wave basis sets, that you don't have to worry about BSSE.
Okay, that's good, because I didn't see what methods you use, but I guess, you know, in the interest of time, you were not able to get into that.
Right. We use DFT D2 as implemented by Grimm, and we use the PBE functional and plane wave basis set.
Okay. You said also, Prof, that your energy increase as the, you know, increase in the energy, or the greater energy means stronger binding. Is it true that then you would use like a dissociative type of reasoning to say, okay, if it takes more energy to take this thing out, is that correct? Then the binding must have been stronger, is that?
Right. So the formula was basically summing up the energy of the gas plus the energy of the ancillary frame of the ants minus the energy of the total system. And of course, when you do these calculations, all those values are negative, and then the energy of the total system is going to be more negative than everything else. So we use that convention to make it, you know, like stronger or tighter binders positive. So that was kind of the formalism that we used. And that's in the literature. Yeah, there's a mix of people who report negative binding energies as being tighter or positive energies as being tighter. It depends on how you decide to, you know, set up your formula. So I would say it's a 50-50 shot. I used what Donald Trular did at the University of Minnesota in one of his papers was to report the Barn-Oppenheimer energies in such a way that more positive is a stronger binder.
Okay. That's very interesting. All right, Prof, I think I'll save the rest for.
Sure. Thank you so much for your questions.
I'm sure you have his email. You can get his email address and further the conversation. Thank you so much. Thank you so much. I'm just here thinking. So you know, the photo that I saw with Professor Cummings and his students, I realized that they were all Black. Okay, we notice these things, yes? And so one of the questions that I have in general is, so Professor Matthews indicated that the demographics is kind of changing. Is it that we now have more Latino type students, and the other question is, do you do any research with undergraduate students? So like that photo you had, Professor Cummings, was that was there any undergrad as a part of that team?
Yes, actually, almost all the students I've worked with are undergrad. I have one master's student, Brittany, and then I didn't name Carrie. She was the other student in there. She's a PhD student, but I started in 2017 and have had 2 grad students, and I've worked with roughly now 12 or 13 undergrads.
Wow.
So I'll have on average 4 to 6 undergrads with us each semester. So hopefully now we don't have the pandemic, they'll be able to spend more time, term in the lab and get more experience. But the demographics are changing a little bit. We do have some more Latina students, Asian students. Like actually, it's not an updated picture, but one of the current students that's in my lab, she's from Nepal. So those are some of the big changes. Dr. Matthews can probably speak more to it because he's been here a little longer.
Okay. All right. Thank you so much.
So when I say the demographic is changing, I'm referring primarily to Washington, D.C., the city. Howard is a HBCU. It's a historically Black college and university. Historic does not mean we don't accept students from all backgrounds. We do. The population of our students, we have a lot of students, as Dr. Johnson said, from the Caribbean, I would say almost every country in Africa. Dr. Morris, who recently moved to the University of Arizona, had a relationship with Puerto Rico. So we had a lot of students coming from Puerto Rico. We've had over the 20 years that I've been here, we've had Caucasian students, Chinese students. They're currently postdocs in the department from India. So in terms of the undergraduate student population, I would say it's probably in the order of 80% Black, but that 80 to 90% Black, but it's a diverse group. It's not just African American, it's Caribbean, it's people from Trinidad, Jamaica, you name every single Caribbean country, every African country. But we also do have a small Indian population. We have a small Chinese population. So it's well represented. It's fairly diverse. We do research with several undergrads. I remember when I first started at Howard back in 2001, every semester I had maybe 6 undergrads in my group. And this was useful for someone like Dr. Johnson. When she was doing her PhD, she would have an undergrad working with her on the project. So it helped her develop good skills in terms of teaching and doing research and, getting an extra pair of hands also. Right now I have 1 undergrad working in my group, but I just hired 5. So the group's about to get a little bit larger.
It's not a voluntary, this is a job.
It's a job, and it's challenging, right? Because the cost of living is high, and students, they'll go to work at Target or Walmart and make money, and that's not helping their educational experience. So what I've done is we've been able to secure a grant to aid in students' research experience. So like this semester, we have some undergrads working in the lab, and they're going to be earning about $3,000 for the semester. They come in, do some hours, and I'd rather them be in a lab working, doing something related to their major as opposed to working at Target selling clothes. I mean, some people have to, and that's how you survive, but if I can help it, I will try to do that. So, and also, as I said, it's useful for the grad students to get that interaction. And the students come to group meeting, and whether the undergrads choose to go to medical school or graduate school, it's a useful experience to work in a research lab.
Awesome, definitely. Great. Thank you so much. All right, so this has really been a very rich discussion, both from the research side and the on the ground side, where the realities of life, and survival and thriving. Clearly this is a very diverse environment, and I really encourage students to look outside of your own sphere. There's so much to learn from other people. And so it's really heartening to know that you do have that level of diversity within your spaces.
And Dr. Gallimore, one more thing, just to interrupt you real quickly. You know, we are in Washington, D.C., so there are a lot of collaborations with other universities. So I believe Dr. Ramadhar has worked with faculty members at GW. I've worked with faculty members at Georgetown. University of Maryland is a short trip up the road. There's Catholic University. We could walk to Catholic. I could walk to Gallaudet University, which is the University for Deaf. I've had students from Gallaudet, which is, as I said, a university for deaf students, and they've come and worked in my lab, and it was really interesting working with them. There's Trinity College. There's a wide, Johns Hopkins is up the road. I think Kanisha, we had a collaboration with Johns Hopkins and the project she worked on. She had the opportunity to interact with Johns Hopkins. It's maybe about 45 minutes on the train up the road. So it's a real, and NIH, there's NIST, a lot of federal agencies. Dr. Raghavan, he collaborates with NIST frequently. We've had Dr. Butcher, who collaborates with the Naval Research Laboratories. NIH is up the road. So it's a really good area to facilitate collaboration. So whatever instruments we don't have, I think Dr. Harris, who's a biochemist, his graduate student utilized all the instrumentation at NIH for his PhD. So we have access to whatever we don't have here.
Wow, awesome, 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 amazing stuff. Okay, well, all is left for me to do is to thank you all for being on this Zoom meeting and discussion. Thank you all for your time. And if you have any questions, Dr. Coley is here. He's the undergrad coordinator. And so undergrad students, you have any questions you want to shoot to him, go right ahead and do so. And of course, any other faculty member, you can go right ahead and shoot some questions to us if you want to get some information on specifically to speak to any of the persons who are here today. You can go right ahead and do so. And that is my encouragement. So let's get out of our spaces and our boxes, because the world should be our oyster, and it is. Yes. So
you're interested in collaborating with us, please reach out to me. I can facilitate that. Dr. Ramadhar didn't talk much about the new single crystal X-ray diffractometer, but
I can give a word. I can give a word for sure.
Go ahead, just let them know what the collaboration could be.
Sure. So we're getting a new single crystal diffractometer. It's going to be a Rigaku instrument, dual source. This would be one of the more powerful ones in the DMV region. And not only that, we were able to get a great deal where they're going to also give us a powder benchtop diffractometer as well. So we're going to get a Rigaku MiniFlex 6th generation. So there's going to be the ability to do single crystal diffraction, and there's going to be the ability to do powder diffraction as well. And one of the things that we're really interested in is really training the next generation of crystallographers. So if you're able to come to Howard, we're going to make sure that you learn how to use the single crystal diffractometer, and the powder diffractometer, so you can do everything on your own. And then Dr. Cummings and I were working on a collaboration with NSF's Chem Mag cars at the synchrotron at the Advanced Photon Source, and we just submitted a grant on Friday. And with this, we're hoping that if we can get it, we will be able to send students to the synchrotron so that they can do workshops, and you can do research at the beamline, so you can learn how to use synchrotron hardware as well on top of doing single crystal diffraction in-house. So I think it's going to be a great training opportunity if you're interested in materials and learning more about crystallography and diffraction science.
Okay, awesome, 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 awesome. And in the chat, Professor Cummings spoke about the concept of fellowships. So there may be opportunities for short-term stays, to enhance that type of an interaction. So with that being said, was my pleasure to be with you all. Have yourself a wonderful rest of your afternoon. And some email addresses are being placed in the chat. So go right ahead and make a note of those. But if you have any other challenges or any issues not getting through to anyone, you can speak to myself, speak to Dr. Coley, as I said, or any other member of faculty. All right, so you have yourself a wonderful afternoon. Thank you all for joining us, and blessings.
Thanks again for coordinating this. Really appreciate it. And if you need any additional speakers, please let us know. We have people who are available to speak. Thanks again, appreciate it.
Thank you so much. Thank you, thank you. All right, have a wonderful afternoon.